there, and welcome to PhD at Living. In my very first video on this channel, I asked you what you thought was the #1 chemical innovation in World War II. I wasn't ready to talk about it at the time, but I am sure ready now. You guessed it, it's the atomic bomb. This series damn near intellectually killed me. Many versions of this story have appeared in a bunch of other media before, so I am absolutely standing on the shoulders of giants to tell my version. I read Dawn Over Zero, Manhattan Project official historian W.L. Lawrence's take on his time on the project from the Trinity test to the bombing of Nagasaki. I read Richard Rhodes' Pulitzer Prize-winning The Making of the Atomic Bomb. I read Critical Assembly, a fantastic and really well-done technical history of Los Alamos during the war years. I even read Steve Sheinkin's young adult book, Bomb. Don't diss it, man. Sometimes going to a 12-year-old reading level really helps. I read half of Wikipedia. Tangentially related, I saw in person both Bockscar and Enola Gay, the two B-29s that delivered the bombs in 1945. I spent more time on this series than all the other videos I have made combined. Through these bad boys, we're going to talk about 68 elements, more than half the periodic table, 32 Nobel laureates, and, by the way, the greatest single scientific achievement of all time. It's hard to understate what the Manhattan Project did for science and, more importantly, the world. I am unabashedly American, so I apologize if this sounds jingoistic at any point. In my defense, however, I will say that many of the principal contributors to the Manhattan Project, Fermi, Szilard, Bethe, Bohr, Einstein co-wrote the letter to FDR begging the United States to start its own atomic research plan, for crying out loud. We're not US born, so that truly makes this a global collaboration. Tyranny threatened to take over the world, and science emphatically, unwaveringly responded. As it turns out, the history here is just as complicated as the science. Nuclear physics in the early 1900s was extremely collaborative, meaning apprentices got passed around like party favors by their masters. Hey, looks like you need some differential equations help. Why don't you go study with this guy over here for a while? Experimental technique honing, eh? Do I have a place for you? It's probably in Germany. With the same names happening here at different times in different places all over the Manhattan Project, it can get pretty darn confusing. I've tried my best to keep it straightforward, but don't say you weren't warned. Because of the insane amount of information here, and to do these topics even a little bit of justice, these videos are going to be about a half an hour apiece. It's a complete departure from my usual format, so get a blanket, put on that adult diaper, and settle in. One final note on names and stuff. I try to pronounce everything correctly here, but sometimes I'm gonna slip up. For instance, in 15 years of being in science, I always said Fritz Haber. In editing these videos, I found out his name is Fritz Haber, so you're gonna hear me, unfortunately incorrectly, say Haber. We're chemists, not linguists, so please be gentle. In summary, I hope this is the most scientific, nitty-grittiest, most complete discussion of the atomic bombs on YouTube. For any of it to make sense, though, we have to start by talking about pudding and some German dude's wife's phalanges. It's 1886. Some people have electricity in their homes, but we only have 75 elements discovered. We also have no idea what an atom looks like or what, if any, parts make it up. This starts the first part to unlocking how nuclear fission became possible in 1938, the structure of the atom. Up to this point, all we knew about atoms was basically what John Dalton proposed in the early part of the 19th century. All materials were made up of elements, and all elements were made up of atoms, the smallest indivisible piece of matter. So at this point, the structure of our atom is basically just a blob. A bunch of blobs make up molecules, and molecules make up everything. In 1897, Brit J.J. Thomson, along with a student named Ernest Rutherford, discovers the electron. Thus, we know there are particles of different charges inside an atom, but the overall charge of an atom is still neutral. The presence of a negative charge therefore necessitates a positive charge somewhere. We just didn't have the skills to find it yet. For Thomson, the explanation to our Dalton atom blob is that there is one big delocalized positive charge in our atom, and the very localized negatively charged electrons are sort of plopped throughout. Thomson being classically British, he called this the plum pudding model. Rutherford starts doing some boss research himself, and with collaborators Ernest Marsden and Hans Geiger, Yes, of the Geiger counter, which, interestingly, an early version of helped this discovery. Discovers the nucleus in 1911. Therefore, because we know there's at least some localization of the positive charge in an atom, Thomson's plum pudding model is unfortunately not correct. So we update our atomic structure to reflect that partially localized positive charge, again with those delocalized electrons just sort of hanging out. While he got the nucleus right, Rutherford didn't perfectly work out how the electrons fit around the nucleus. Japanese physicist Hontaro Nagayaka suggested a nucleus-based version of the atom with the electrons sort of like rings around Saturn. The problem with that is that Saturn's rings are held together by gravity, an attractive force, and the like negative charges of electrons are clearly repulsive. The big discovery here was by Dane Niels Bohr, while working for Rutherford, resolving the electron problem with a quantum mechanical explanation instead of a classical mechanics explanation in 1913. The classical mechanics explanation dictated the electrons by gravity, which therefore would make the atom unstable and the electrons would eventually crash into the nucleus. This not being the case, atoms spontaneously blowing up and such, we had to have a different explanation. Bohr brought together theory, namely Planck's version of quantized energy, E equals h nu, and experiment, Rydberg numbers, that is, electrons from certain atoms have extremely characteristic spectral emissions, by showing electrons could only exist at certain states at a certain level of energy. This also meant electrons had a ground state, meaning they were pretty stable, and explained why atoms didn't just disintegrate by themselves all the time. This means that atoms and electrons in general are not dictated by classical theory, and in fact are dominated by quantum physics. This same section of Bohr's theory explains a lot of Vesper theory and why some elements are similar to other elements in the same group. As the size and charge of a nucleus gets bigger, those inner electrons are held that much more tightly and shield the outer or valence electrons. Those valence electrons then can give the chemical characteristics of an element in question. Keep all this in mind because it becomes important a couple episodes down the road when we talk about trying to fractionate or co-precipitate or otherwise separate a given elemental isotope by using a similar but not the same element as a surrogate for it. In that same year, 1913, Thomson discovers the first isotope of a non-radioactive atom. Up to this point, we've only been talking about atoms and their charge, but there is another equally important component of it, mass. Thomson was looking at different neon atoms, and they behave differently with the only difference being their mass. Therefore, the same element can have different masses. We don't know why yet, but we're getting there. Because we don't know how certain atoms of the same element can have different mass, and because we don't have a full periodic table yet, this field is the Wild West. Especially at the high atomic number ranges, anything discovered that doesn't have identical properties to something already known is considered a brand spanking new element. Unfortunately, it's almost always just an isotope of an already known element. You can see how this gets confusing. Fast forward to 1917, and Rutherford discovers the proton. Now we know that this somewhat localized positive charge as an atom is composed of a number of individual small proton pieces, kind of like how the negative charge in an atom is composed of all those electrons. But here's our problem with mass again. We know the protons live in the nucleus, and each proton has an atomic mass of 1, and the electrons just sort of float around the outside, and each of those weighs effectively 0. But when we weigh our atoms, we see, like here, a helium atom that has 2 protons, but it weighs 4. And if we measure a nitrogen atom with 7 protons, it weighs 14. So what's going on here? Well, a couple silly reasons were proposed, including one that said there were more protons in there that we just couldn't see, and also that meant there were more electrons in there to keep the charge of the atom neutral, and we just couldn't see those either because of reasons. This whole thing never really jived with Rutherford, and he proposed the neutron, that is an atomic species with no charge but 1 mass, in a speech in 1920. The problem there is the theoretical properties of the neutron said it would be a very fickle beast and extremely difficult to see. In fact, it took 12 years, culminating in 1932 when James Chadwick, who's working for Rutherford by the way, completes the puzzle with official proof of the neutron. Chadwick's experiment was a direct application of one Irene Joliot-Curie had been doing in France a short time before, and involved hitting beryllium atoms with alpha radiation from polonium. Essentially, Joliot-Curie was seeing the radiation produced from this and said it was gamma radiation. However, Chadwick saw the energy and correctly identified it as the fabled neutron. Remember this beryllium-polonium thing. It becomes mighty important later. The discovery of the neutron finally gives us a way to describe how the mass of an atom, even if it has the same number of protons and electrons, can change while maintaining that overall neutral atomic charge. This explains how isotopes exist, what the structure of an atom actually is, why one element does something different from another element, heck, why elements are elements in the first place, and a whole host of other things. So, in summary, pre-Thomson, the best we had for the atom was a big blob. Thomson comes along in 1897, discovers the electron, and gives us the plum pudding model. Rutherford nails the proton years later and has the nuclear-based version, but the electron cloud is still kind of messy. Bohr comes through with quantum mechanics and describes the electron orbitals, and Chadwick confirms the neutron in 1932, giving us basically the whole structure as we know it. And let's describe that whole structure with a really simple example. Let's look at hydrogen. Hydrogen 1 is just a single proton in the nucleus, no neutron. And there's an electron that, per Bohr's quantum theory, sort of just floats around the outside, which we represent as a simple ring. Not the rings like Saturn's rings that we talked about before. To fill out that third particle, let's add a neutron in here to hydrogen and make it hydrogen 2, or deuterium. Now we can see our full structure of the atom. We have a very small localized area of the nucleus that has both the charge and the mass of the atom. We have our 1 weight, 1 charge proton and our 1 weight, 0 charge neutron. In addition, we have a fairly delocalized area of negative charge where the electron just sort of floats around in some quantum mechanics statistical way. There's a lot more that goes into the electron delocalization, and this is definitely a gross oversimplification of it, but it's the best we have without going really far into the weeds. Now let's move to the second part of our explanation on nuclear fission. What happens to atoms when they give away pieces of themselves? Because of where we are in modern science, it's not hard for people to accept that there are things we can't see but are actually there. Back in the day, however, this was a mind-blowing discovery when a previously invisible thing was shown to actually exist. So it was in late 1895 when German physicist Wilhelm Röntgen discovered X-rays. The scientific world was aflame at the discovery, and Röntgen debuted it by showing a radiograph of his wife's hand, where you could see the bones inside her body. Not a year later, French physicist Henri Becquerel was trying to correlate his studies on phosphorescence with Röntgen's novel discovery of the X-ray. Becquerel noticed that uranium and uranium salts also emitted invisible rays, but Becquerel's rays weren't X-rays. Becquerel's rays came from radioactivity. There's a key distinction here. X-rays have to be generated by an external source, while radioactivity happens spontaneously. Initially, Becquerel would expose his samples to sunlight and then put them up against a photographic plate to phosphoresce. One day, however, the sun wasn't shining, so Becquerel just took his sample in his phosphorescent plates and threw them in a drawer somewhere, left him in the dark for a couple days. Even though he wasn't expecting anything, Becquerel developed the plates a couple days later, and to his surprise, noticed there were spots on the plates! The interesting thing here is Becquerel didn't expose his samples to any external excitation source, so the rays had to be developed spontaneously. This is how Becquerel knew that his rays weren't phosphorescence or X-rays. After a little more work, Becquerel discovered that radioactivity was a lot more complicated than X-rays, but he didn't have a handle on why. Keep in mind this is a year before the electron was discovered, so we had a long way to go before we figured out radioactivity theory. As a side note, this is an excellent example of serendipity. In order for an accidental discovery to be made, the mind has to be prepared enough to observe the unexpected result and have a reason to go further. To quote Louis Pasteur, "In the fields of observation, chance favors only the prepared mind." Becquerel's discovery wasn't happenstance because he knew enough to know the result wasn't spurious. Over the course of the next year, Becquerel, along with two unknown scientists named, Pierre and Marie Curie, discovered that thorium was radioactive and straight up discovered the elements polonium and radium. Becquerel and the Curies were thusly awarded the Nobel Prize in Physics in 1903. And now our main character for this part of the story enters, and he's a young German scientist named Otto Hahn. Hahn, in 1904, first studied under William Ramsay, the guy who discovered all but one of the noble gases, everything but radon, helium, neon, argon, krypton, and xenon. In the late 1800s. Ramsay studied under John William Strutt, aka Lord Rayleigh of Rayleigh scattering fame and stuff. Ramsay and Rayleigh were awarded the Nobel Prize in Physics in 1904 for that discovery of almost all the noble gases. Back to Hahn. During his career in radiochemistry, Hahn discovered a number of new elements, including radiothorium, thorium-C, radium-D, and radioactinium. Unfortunately for Hahn, these weren't actually new elements, they were just previously unknown isotopes of previously known elements. It was still 30 years before the discovery of the neutron, so that list, for what it's worth, is thorium-228, polonium-212, lead-220, and thorium-227, respectively, for those of you playing at home. Can you imagine doing fundamental scientific research in 1904? That Hahn was able to tell the difference from radiothorium to regular thorium blows my effing mind. I have trouble at work making sure I don't cloud polycarbonate by rubbing acetone all over it. Hahn, however, did so well with Ramsay that in 1905, Ramsay suggested Hahn go study in Montreal with none other than Ernest Rutherford. Let's talk about Rutherford right quick. He was a scientific badass and is either directly or indirectly responsible for a number of the critical pieces to nuclear fission. To wit, Rutherford first studied under the venerable J.J. Thomson, he of the unfortunately incorrect plum pudding model of the atom, but of the absolutely correct first stable isotope discovery and the fundamental first mass spectrometry experiments. Nobel Prize in Physics in 1906 too, by the by. Thomson's main discovery for our purposes, however, is that of the electron in 1897, which was done when Rutherford was part of his lab. After leaving Thomson's lab and working at McGill University in Montreal, Rutherford discovered alpha and beta radiation. Alpha radiation is a helium nucleus, 2 protons, 2 neutrons, no electrons. Beta radiation comes in one of two forms. Either you basically convert a proton into a neutron, or you convert a neutron into a proton, with some other junky stuff. Remember that at the time we didn't know any of this for a few more years. Rutherford just knew that alpha particles and beta particles, whatever they were, penetrated to different depths. He also discovered the last noble gas radon and confirmed the existence of the nucleus. This is the famous gold foil experiment you heard in Gen Chem, where Rutherford realized that the positive charge in an atom was localized in a very small part, and the negative charge in an atom was delocalized and just sort of floated around the positive charge to keep all the stuff balanced. You probably heard about this when you learned it in the driest way imaginable. Some molecules bounced off the gold foil, suggesting there was localized mass causing them to deflect. Snore. I'd like to think if your professor said something like, "Hey, Rutherford's gold foil experiment helped us win World War II," that a little more ears would perk up and people would listen. And hey, honestly, that's why I'm telling you all this stuff. One more rabbit trail, but if you don't like rabbit trails, I'm not sure why you ever stuck around. I should have just named this channel Devin's Random Tangents that he likes and hopes you can follow. Anyway, scientist Frederick Soddy bounces around in this story almost as much as Otto Hahn does. Soddy worked with Rutherford in Montreal during the alpha and beta radiation days, so he was instrumental in showing that elements transmutated into other elements by throwing off characteristic pieces of themselves, regardless of what element started it. Previous to this, we had no idea how radioactivity actually worked. Then Soddy went to work for Ramsay, remember him? On noble gas stuff, and then moved to the University of Glasgow. Remember how I said J.J. Thomson discovered the first stable isotope? Yeah, I specified because Soddy discovered the first radioactive isotope, and in fact used the term isotope first. Finally, Soddy discovered that alpha radiation caused the loss of 2 atomic numbers. We knew with radiation like that, atoms could change into other atoms, but we weren't exactly sure what pieces were coming or going. For his sweet work in radiochemistry, Soddy was awarded the Nobel Prize in Chemistry in 1921. Back to Otto Hahn. He returned to Germany in 1906 and continued working in radioactivity until the start of World War I. During the war, Hahn was actively involved in chemical warfare and at one point met Fritz Haber, he of the nitrogen fixation process and the father of chemical warfare. That's for a different video, however. During the war, Hahn was unfortunately poisoned by probably phosgene gas, one of those no joke, always nasty, never good for you ever compounds. During this time back in Germany, Hahn became great friends and collaborators with Austrian scientist Lise Meitner. In the 1917-18 timeframe, Meitner and Hahn discovered the most stable form of protactinium, protactinium-231. while Casimir Fajans and his student Oswald Gering discovered protactinium first with protactinium-234 in 1913, Hahn and Meitner are often, incorrectly, given credit. And now the story brings us to our next character, Lise Meitner. She was the first woman who Max Planck, he of quantum theory and Planck's constant and stuff. Planck worked for Helmholtz for a while and frequently hung out with Einstein and Otto Hahn pre-World War II. In a crazy twist of fate, Planck's son Erwin was part of the 20 July plot to kill Hitler and was unfortunately executed by a kangaroo court in 1944. Allowed to attend his lectures at the Humboldt University of Berlin, and eventually she became his assistant. Meitner discovered the Auger effect in 1922. Why isn't it called the Meitner effect? Well, outdated chauvinistic modalities, it seems. While Auger discovered it independently a year later, it's named for him probably because he's a man, and probably because it was the bulk of his research, whereas for Meitner the effect was just kind of a happy side effect. For what it's worth, Meitner ended up getting her name on one of the elements, meitnerium, so that's a pretty darn good consolation prize. In 1926, Meitner became the first female full professor of physics, say that 5 times fast, in the entire country of Germany. During this time, she gave a sample of polonium to James Chadwick, he of the neutron discovering thing. Incidentally, Chadwick was awarded the Nobel Prize for Physics in 1935 for his discovery. And now our stories converge. In 1933, we have a fairly good idea of the structure of the atom, and we know that certain atoms are radioactive and give off particular pieces of themselves in fairly predictable ways. Putting these ideas together, it was theorized that you could take a whole stable atom and bombard it with pieces of an atom to induce radioactivity. Hang on a sec here. I got you that some atoms will spontaneously decompose through radioactivity, but who decides whether an atom is going to decompose or not? Damn! Excellent question. To get the answer though, we're going to have to go on a heck of a detour, so buckle up, baby! This one's going to be rough! Here's a really easy concept to grasp. 2 protons don't like each other. Having 2 positive charges this close together creates significant electromagnetic repulsion. However, there's a secret cheat code in nuclear physics called the strong force. At a distance of about 1 femtometer or less between subatomic nucleons, that is protons or neutrons, the strong force is strong enough, as the name suggests, to overcome any electromagnetic repulsion between these particles. Therefore, the strong force is what keeps protons, and to a larger extent nuclei in general, held together. With that, let's make some atoms. Hydrogen has a single proton and no neutrons. Easy peasy. But helium has 2 protons and they don't like each other. Even at this distance though, the strong force should be enough to overcome that electromagnetic repulsion. The real answer, if you want to get technical, is the strong force is not enough and combines with the Pauli exclusion principle to make helium-2 unstable. Here's where the fun begins. If we take poor unstable helium-2 and add to it a neutron, the increased strong force, along with no increased electromagnetic repulsion, after all, neutrons are in fact electrically neutral, means that helium-3 is stable. As it turns out, helium-4 is the most stable form of helium because of quantum theory. You pair the spin of the neutrons. It's not like a literal spin, it's more like an approximation of angular momentum and a bunch of other quantum physics. It's well beyond the, oh no, now I've gone cross-eyed. Up to an atomic number of 20 or so, atoms like to have the same number of protons as they do neutrons. Above that number though, as you increase more protons, you need to add more neutrons as well. The reason is the increased strong force of each neutron is needed to overcome the electromagnetic repulsion of all those really closely packed protons. If you throw this ratio, and for a given atom there's a good ratio of protons to neutrons out of whack, either by adding a whole bunch of new neutrons, taking a whole bunch of neutrons away, or otherwise, the atom can tend to throw a piece of itself off in a decay. It'll even throw pieces of itself off to change into a different element in order to regain that stability. This decay, my friends, is radioactivity. Somewhat relevant to this, above uranium's 92 protons, there is no amount of neutrons that can bring balance to the force. Therefore, every element with more than 92 protons is inherently radioactive and looking to shed a piece of itself to regain atomic stability. In this context, induced radioactivity is taking a perfectly happy atom, let's say uranium-235 or uranium-238, and disrupting the whole thing by adding a proton or a neutron. At one point, a coworker asked me how the strong force works, and I replied, I don't have any idea! Why are you asking me this? After my Xanax, I was able to read up about it a bit, per usual expecting a pretty straightforward answer. And this is why I'm an idiot. I was trying to figure out fundamental particle physics in like 5 minutes. 5 days of furious Wikipedia-ing later, here's my answer. The strong force, weak force, and electromagnetism are the 3 forces of the standard model of particle physics. These 3 forces are called bosons and hold together the 12 elementary particles of the standard model. But wait, aren't the smallest pieces of matter the proton, neutron, and electron? For 31 years, I sure thought so, but nah, my buddy Walt had to ask the question and ruin everything and make me discover the up, down, cute, strange top and bottom quarks and the electron, neutrino, muon neutrino, tau, and tau neutrino leptons. The electron, thank God, is one of the leptons already, so I only had to learn the other 11. Basically, the strong force is the way it is because of these things. Well, why do bosons have force? Because they have angular momentum. But why do they have angular... They just do! You've reached the cutting edge of particle acceleration research in 2020! Congratulations! If you really want to dig in, I have posted in this video's description a bunch of Wikipedia articles for particle physics and posted a nice video from Fermilab about the standard model. Outside of that, I cannot explain it. You have broken me. Can we just keep talking about protons and neutrons, please? While protons and alpha particles were the first bullets, if you will, neutrons turned out to be the best thing to smack atoms with because the neutral charge allowed them easier access into the nucleus at relatively lower energies. And cooler than that, the speed, and therefore energy, of a neutron changed the way the atom it hits reacts. In another beautiful piece of scientific serendipity, Italian physicist Enrico Fermi realized that atoms would radioactively decay in different ways if he ran the same experiment on a marble table compared to a wooden table. Much more on Fermi and fast and slow neutrons later, but we gotta finish this part of the story first. For a small element, smacking it with a neutron usually just blows a piece off. For a big element, however, smacking it with a neutron usually results in that neutron being soaked up into the bulk. This, however, results in a large energy increase that needs to be resolved somehow. The somehow in this case is a form of beta radiation wherein a neutron becomes a proton. You'll notice that by increasing the number of protons in the element isn't that element anymore. For an element like uranium, atomic number 92, and the largest naturally occurring element, that gain in 1 proton would result in the element having 93 protons and would be a brand new man-made element. It's not that crazy to think about because we've added 20 or so synthetic elements in the last 75 years, but at the time, this was like alchemy. You go, oh, I'm just going to add my neutrons and stuff, make a whole brand new element. This whole make a new element thing started a race among Meitner and Hahn in Germany, Rutherford in England, Fermi in Italy, and with Irene Joliette Curie, daughter of Pierre and Marie Curie, in France. This whole hunt for transuranic elements was considered esoteric at the time, but within a decade it would change the world forever. Because being Jewish was a crime in Nazi Germany, many prominent scientists left Hitlerland for greener pastures and less abject racism. Meitner stayed behind, but eventually lost the protection her Austrian citizenship provided her in the Anschluss of 1938. She found her way to the Netherlands and eventually Stockholm, where she took up a working relationship with our good friend Niels Bohr. Analogous to Rutherford being the experimental godfather of nuclear physics, Bohr just keeps popping up everywhere as the theoretical godfather of this whole thing. Bohr, Meitner, Hahn, and Meitner's nephew, Otto Frisch, all met in Copenhagen in November 1938 to discuss radiochemistry and probably how messed up that whole Nazi thing in Germany was. A month later, Hahn and his assistant Fritz Strassmann definitively proved nuclear fission for the first time. While bombarding uranium with neutrons, looking for elements with more than 92 protons, Hahn discovered that there was previously not there barium, 56 protons. While the only explanation was that the barium had come from the uranium, Hahn just couldn't believe it. Listen, it's a previously unthinkable concept that you could actually split the atom. Heck, even Einstein didn't believe it was possible. All that information went from Hahn to his good friend Lisa Meitner. Meitner and Frisch on a winter's walk in the snow, like something out of a fairy tale, if fairy tales had PhDs platonically discussing nuclear theory, a girl can dream. Used Einstein's theory of relativity, that is E equals mc squared, to describe the relationship between energy and mass. Essentially, when a uranium atom splits, it turns into a barium atom and a krypton atom. It also makes some neutrons, which again, nobody knew existed 6 years before this theory was developed, and an absurd amount of energy. If you count everything up here, there's some protons and neutrons missing, but they haven't just disappeared. And this is the secret to the atomic bomb. Nuclear fission converts mass into energy in a way no other chemical process does. When you split the atom, the energy released is 3 billion times higher than the hottest exothermic reaction that splits molecules. Anywho, Meitner and Frisch calculated the amount of energy that would be released if a uranium atom was in fact split. After this amount of energy was experimentally verified, it was decided nuclear fission was in fact both real and achievable. Richard Rhodes does a really good job describing a lot of these experiments through the late 1800s and up to Hahn and Strassmann's discovery of nuclear fission in 1938. These experiments are elegant. Oh my goodness. I spent 6 years fumbling around in grad school, and I don't think I ever made a single experiment that was as good as any one of these experiments. They are rigorous, they are methodical, they are logical to a fault, they're pretty much unimpeachable. Even with that, the results of these puppies were so outlandish that the people getting the results had a hard time believing them and thought they'd be ridiculed when they published them. In 1939, the Joliot-Curies in France proved that fission does indeed create neutrons. While this is a pretty solid achievement, they just missed out some of the big ones. They missed the positron, they missed the neutron, and they missed the big one, nuclear fission. Just by a little. They were still awarded the Nobel Prize in 1935 for inducing radioactivity in lighter elements, but that still has to sting a little. They're basically the Sammy Sosa to Chadwick and Hans Mark McGuire. Not sure any of them took roids, though. To finish Meitner's story, she was asked to participate in the Manhattan Project in the 40s, but politely declined. Dude, this history lesson has been enthralling, but where is the bomb in any of this? Fair. I was getting there right now anyway, so don't think you influenced me. We've been talking about how nuclear fission releases an insane amount of energy, and that's well and good, but it's not like a single atom is going to take down a city. The key to that solution is in the concept of a chain reaction. And no, not the Morgan Freeman Keanu Reeves movie. A chain reaction happens when a product or byproduct of a reaction starts an additional reaction. Think of how rabbits multiply. 2 rabbits create an Australian pandemic in like 4 minutes. Chemical chain reactions had been around for some time, but nobody had ever applied the concept to nuclear fission. Incidentally, Ernest Rutherford, he's everywhere, may be directly responsible for the theory of nuclear chain reactions. 2 of Rutherford's students were bombarding lithium-7 with protons in order to induce alpha decay. In a published speech, Rutherford said the process's efficiency wasn't very high, and in fact, anybody who thought nuclear chain reactions could be efficient enough to be used as power sources was drinking moonshine. Hungarian physicist Leo Szilard read this and made an interesting connection. If instead of a proton, a neutron, and I'm sorry to keep hammering this, but it had just been discovered, could start the reaction and neutrons were produced as a product, then a nuclear chain reaction could be possible. The big key here is that Szilard did not propose that the neutrons would be created from a nuclear fission, that is, an atom breaking down into smaller pieces. A year later, Szilard patented a non-fission chain reactor with his co-worker Enrico Fermi. And here we are. It's 1938, and we know basically the complete structure of the atom and its relevant pieces: protons, neutrons, electrons, etc. We know that you can radioactively decay elements and have them throw off pieces of themselves. Alpha particles, beta particles, neutrons, sometimes fission into completely different atoms. And we know that if neutrons both cause and are a product of nuclear fission, you can create a nuclear chain reaction that creates unprecedented levels of energy. Szilard did some rudimentary experiments and showed uranium almost certainly could propagate a nuclear chain reaction. With the knowledge that the nuclear chain reaction was possible, and that the Nazis almost certainly knew this, Szilard tried to convince the US government to put more time, energy, and resources into investigating that possibility. With help from his friends Eugene Wigner, member of the Manhattan Project and Nobel Prize winner in physics in 1963, and Edvard Teller, total boss, co-founder of the Lawrence Livermore National Lab, the Teller part of Brunauer-Emmett Teller theory, member of the Manhattan Project, and father of the hydrogen bomb. Szilard enlisted the help of world-famous Albert Einstein to get the ear of FDR in August 1939. After reading the contents of the letter, the president was sufficiently concerned, and over the next couple years, a number of working groups and committees were established to investigate nuclear weapons. In England in 1940, Otto Frisch, remember him, and Rudolf Peierls, who studied with Werner Heisenberg, Wolfgang Pauli, Enrico Fermi, and Hans Bethe, which, with the free space, gives him ludicrously good scientist bingo! Calculated pure uranium's critical mass, that is the amount of material necessary to sustain a nuclear chain reaction, at about 25 pounds. That number really got the British government interested in investigating nuclear weapons through the establishment of the Maud Committee, on which James Chadwick, discoverer of the neutron, served. This eventually became the British nuclear project known as tube alloys. Up to 1941, the British did the heavy legwork in atomic bomb research, including calculating critical masses and looking at slow fission probabilities. The US saw this research, but kind of dilly-dallied around and didn't do anything with it. In the meantime, the National Defense Research Committee was established and run by Vannevar Bush at MIT and James B. Conant, president of Harvard. Bush wisens up after a while and realizes he needs a wider breadth of coverage, so he creates the Office of Scientific Research and Development, OSRD, and subsumes the NDRC. Conant becomes in charge of that. What really gets the American bomb project going, however, is Australian Mark Oliphant from the British project flying over to Berkeley, California to convince physicist Ernest Lawrence. More on him in episode 3. To hit this whole nuclear fission atomic bomb thing a lot harder stateside. Lawrence is thoroughly convinced and talks to Arthur Compton, professor of physics at the University of Chicago, Nobel Prize winner in physics in 1927, and head of the metallurgical lab in Chicago. Vannevar Bush talks to Compton and gets him to be in charge of the majority of the nuclear research in the United States in the early 1940s, with the Met Lab's charter of go out and do plutonium and atomic bomb stuff, which I promise we'll get to way later. Compton in turn talks to George Kistakowski, also more on him later, at Harvard. Kistakowski talks to Conant, and Conant gets the whole ball rolling. With that, the British atomic bomb project is absorbed into the ramped-up American effort. On 28 December 1942, FDR finally, mercifully, ends this part of our discussion with the creation of the Manhattan Project. As crazy as it sounds, the story in real life is way more complicated and convoluted than even I'm telling it, but you don't want to hear any of that. Thanks for bearing with me. I absolutely did not expect this episode to take this long, but I didn't know all the fun scientific connections we'd make. Anyhow, we have our roadmap for the Manhattan Project. Number 1, we need enough uranium for a bomb. That happens in Oak Ridge, Tennessee. Number 2, we need enough plutonium for a bomb. This happens at the Metallurgical Lab in Chicago and in Washington State at the Hanford Lab. And number 3, we need the bomb. This, of course, happens at the secret lab in Los Alamos, New Mexico. The next step in our process, however, is proving that a nuclear chain reaction is actually possible. But that's for then, and this is for now. See you next time! Heck, I reckon you wouldn't even be human beings if you didn't have some pretty strong personal feelings about nuclear combat.